Today I'm going to present a theorem that I find cool. It's called Stein's restriction theorem. Suppose we're given a function in LP with p in between 1 and 2. Using interpolation, we can show that the Fourier transform f hat of f is in LP prime, with p prime being the conjugate of p. If we look at the unit circle gamma in R2, we know that it has zero Lebesgue measure, whereas LP functions are only defined up to sets of measure 0. So a priori, it doesn't make sense to restrict f hat to the unit circle. However, the theorem by Stein tells us that a dense subset of LP, namely the smooth functions with compact support, can in fact be restricted to the unit circle in the sense that the L2 norm of their Fourier transform restricted to the unit circle is bounded above by a constant depending on p, and the LP norm of f, with p having the following range. This will become clear once we finish the proof. The proof relies on three components. The first one is Holder's inequality. The second one is generalized Young's inequality. And the third one is the decay of the Bessel function. First, we write the left-hand side in the squared in the following form. If we let U denote the restriction of the Lebesgue measure on the unit circle, then the integral becomes the following. Note that we have changed the domain of integration from the unit circle to R2, but added the U to the integrand. We can now write this in the inner product form because we're in L2. Using Plancherel, this is the inner product between f and the following convolution. Namely the convolution between f and the Fourier transform of the measure. Now we apply Holder's inequality. And we further apply generalized Young's inequality to the second term. Here, P and Q satisfy the following equation. But we should ask ourselves, when is the Fourier transform of the Lebesgue measure on the unit circle in LQ? So the decay of the Bessel functions tells us that this term here is finite whenever Q is strictly bigger than 4. Because of this relation, we know that the term here is in fact a constant depending only on P for fixed P. And we have thus proved the theorem. Using the requirement that Q is bounded below by 4, we can actually prove the corresponding requirement on P. So I'm applying to the Courant Institute because I want to obtain a PhD in mathematics. And the reason for that is because I simply find math very interesting, and I want to learn more about the interplay between math and physics. And I think Courant is a great place because it has a very strong program in analysis and related fields, and that's what my current interests are. And there are a lot of faculty members working in this field, and Courant just has a very strong academic reputation, and so I think it would be a good place for me to do my graduate studies. Thanks.